Hello, I welcome you all in this course on power plant engineering. Today we will discuss about the steam condensers. Topics to be covered today are the function of condensers, cooling systems, classification, requirements of a good condenser, condenser vacuum. Now the function of condensers, as you know, if you draw again the Rankine cycle on temperature entropy diagram, then again it is 1, 2, this is expansion in the turbine, and 2 to 3 is condensation, the condensation of steam, then 4, 3 to 4 is pumping, and 4 to 1 is boiler. Now the steam is condensed in a condenser where the process 2 to 3 takes place. As we know, if we keep on reducing this pressure, right, we will be getting the more energy, more output. If we draw this process in enthalpy entropy diagram, this is saturation line, x is equal to 1. So if we keep on expanding this constant entropy process, if we keep on reducing the pressure, we will be getting the more output. If you compare this PV diagram of a reciprocating compressors, reciprocating steam engine, it is like this. And if you draw on a PV, on the PV pressure and volume diagram, if you draw the diagram for the steam turbine, it is also like this. Pressure and volume, right? Now this is an ideal diagram. Actually, I have not shown in reciprocating compressor, I have not shown any clearance here. In fact, there has to be clearance between the piston head and the cylinder head. In that case, there will always be a cushion of the steam, and the ideal diagram is going to be like this. This is 1, 2, 3 and 4. 1, 2, 3 and 4. Ideal diagram is going to be like this for the steam engine, 1, 2, 3 and 4, right? But it is none of the concern here. Here the concern is, if we keep on reducing the pressure, this back pressure in a steam engine or in a turbine, the exit pressure of a turbine, we will be getting more power because the area of PV diagram will increase. But here in the steam engine we do not do this, because if you look at the later part, it is a parabolic process, PV is equal to C. It is not constant temperature process. This expansion process is parabolic process, PV is equal to C, and the expansion goes like this. So in the fag end, if you look at this end, we are getting very less power output, and maybe this output may be compensated by the friction loss in the engine, reciprocating engine. So normally the output is not, expansion is not taken up to here, it is taken up to here. So the diagram is like this. But in the steam turbine we can keep on expanding because it is a rotary machine, right? We can keep on expanding up to absolute vacuum, or absolute pressure is 0. But that we normally do not do. Even we restrict this pressure to a certain value in turbines. The reason being, the cooling is done by the water, and the water is taken from some river or from some water body, right? And this water is at the normal temperature. Temperature may vary from say 20 to 30 degrees centigrade. So this water is used for the cooling purpose, for the extraction of heat. So if the steam temperature is lower than this, in fact the steam will be getting heated rather than extraction of heat is taking place. So the temperature of steam has to be higher than this value, and at least 10 degrees centigrade higher than this value. So if we look at the values, if you take 10 kilopascal pressure, suppose pressure in the condenser is 10 kilopascal, corresponding saturation temperature is 45.81 degrees centigrade. If the pressure is 7.5 kilopascal, the temperature is 40.33 degrees centigrade. This is just to give you physical idea about the quantities, right. So, the pressure, normally pressure in the condenser of this order only. Now, if I increase this pressure, if I increase this pressure, I take it to 20 kilopascal. Saturation, this temperature will shoot. But when we increase this pressure, in that case output of the turbine will reduce, right. At the same time, size of the condenser will also reduce because LMTD will increase. Q is equal to U LMTD or AMTD, whatever is applicable here, LMTD or AMTD multiplied by area, right. So, when this LMTD is increasing because we are condensing at higher temperature, right, area will reduce for the same amount of heat restriction. And if we reduce this, it means we come to 40. When we come to 40 or we further reduce the pressure, the output of the turbine will increase. At the same time, area has to be increased. LMTD will reduce, area has to be increased enormously, right. So, the fixed cost of the system will increase. And beyond a certain value, it is not possible at all. We cannot go beyond 7.5 or 10 kilopascal because our cooling water is available at 25 to 30 degrees centigrade, right. Now, we will talk about the advantages of condensers. This is the importance of a condenser I have explained you in a system. Now, advantage of the condenser, it improves the efficiency of the system, right. Recovers the condensate, condensate. It means there is a closed loop. So, after the condensation, again it can go to the boiler and the closed loop the system can work, but still due to some leakage or many, because in condenser also steam is vented out in order to remove air. I will discuss it later on. So, compensating water is required and it is 1.5%. Make-up water is approximately 1.5% of the total water requirement, right. Now, it reduces the steam consumption also. From the same, suppose power requirement is same, if per cycle output is more, definitely we will have to use less amount of steam. For example, suppose 73.1 corresponding to 73.1, this is 94.7 and 71.0, it is 98.0 kilopascal pressure. 73.1 is centimeter of mercury. If we change pressure from this to this, we can increase output by 6%. This is simple, a rough calculation to have some idea about the pressures. So, slight variation in pressure may affect the efficiency or the output of the entire system. Now, if there is a closed loop, say water is always under a heated stage, right. If you compare with the water which is fresh water which is coming at 20 or 25 degrees centigrade and the water which is available in the closed loop is available at 45 degrees centigrade. So, this will also reduce the thermal stresses in the system, right. So, in a closed loop the thermal stresses in the system also is reduced and closed loop is attained by using a condenser. And water softening plant, because if you use a water softening plant which is require because we cannot just simply put the water inside the system because scaling will take place in that case. So, in order to remove that, water softening plant is used. If we are using fresh water for entire process, then the size of the water softening plant will increase or the load of this water softening plant is increased, because in this case when it is a closed loop using condenser, the make-up water is only 1.5%, right. So, this cost will also increase in a power plant. So, the condensers, there are two types: water cooled, and air cooled. Air cooled condensers are also there when there is a scarcity of the water. Air cooled condensers are also used. There are direct type and indirect type. There are different type of air condensers. So if it is a water cooled condensers, if you remember that in a thermal power plant, 60% of the heat is taken away in the condenser, because heat is added in the boiler, expansion in the turbine, and in the condenser approximately 60% of the heat is taken away. The water consumption, I just want to tell you the magnitude of the water consumption in a power plant. It is approximately 5 to 8 kg per kilowatt hour. This is the amount of water consumption water is required in a thermal power plant. Or suppose there is a 2000 megawatt thermal power plant. In this power plant, we require 240 kilotons of water per day, or 24000 tons of water per day. So water requirement is huge in a thermal power plant, right? And at the same time, heat rejection is huge in a steam condenser. And there are different elements of of a condenser. One is dry air pump. This pump is used to remove air from the condenser, because air does enter the condenser because it is operating at subatmospheric pressure. There may be some leakage through the cracks, or air also comes with the water, makeup water in the condenser. So air has to be removed, right? So dry air pump is used. Now another is cooling water pump, because water has to go inside the condenser. So there will not be any gravity flow. A pump has to be used. A pump house is there which pumps the water into the condenser for the cooling purpose. And while designing a condenser, it has to be ensured that the temperature rise of the water should not be more than 10 degrees centigrade. Because this also is a closed loop. We do not have infinite amount of water. Cooling water is also finite. The working fluid is also finite. So what happens, this water which is emerging from the condenser, right, it goes to a cooling tower, and where the cooling of water takes place by natural process, and during this process the maximum temperature drop is considered to be 10 degrees centigrade. I mean, this is for the design purpose, right? So this is a restriction in designing of a surface condenser, that the mass flow rate or the size of the condenser. So how it will be compensated? Q is equal to mCp delta T, right? This is so certain amount of heat has to be carried away. Delta T we have fixed, Cp is also fixed. So we have to monitor the mass flow rate. Mass flow rate means how many number of tubes are required, what should be the size of the condenser, right? This has to be decided by this. So that is, we are talking about the cooling water pump. Then feed water pump. Feed water pump is there. Cooling tower or spray pond is there. This is an integral part. There are certain relief valve. And there is a makeup water pump. Relief valves are to be in any machine. I mean, whether it is pressurized, in any pressurized machine, two relief valves have to be provided. And here also there is a relief valve for removing air. I mean, sometimes air has to be removed, as I said earlier. The relief valve is used. It is not a safety valve, it is simply a relief valve which is provided in the condenser. Now, there are jet condenser which are known as the direct contact condenser. So I mean, there are two types of condenser where coolant and the fluid, they do not come into the contact, like surface condenser. There are certain condensers where fluid and the coolant, they get mixed. They are known as jet condensers or direct contact type of condensers, right? Then again we can classify downflow condensers, invert flow condensers. This is about the surface condenser. So normally they are jet condensers. and they are surface condensers, and evaporative condensers are also there, right. So, in jet condensers there is a direct contact of coolant and the steam which is coming from the turbine. So, in jet condenser we will talk about the low level jet condenser. Low level jet condenser, right. In low level jet condenser there is a column, in low level jet condenser there is a column, right, and at the bottom there is a condensate pump which put the condensate into the hot well, right. And because we are talking about the counter flow type, so the cooling water enters from here and steam enters from here. So, steam is entering from the bottom and it is moving in the upward direction, cooling water is coming from here, it is moving in downward direction. So, mixing takes place, and finally what happens, because cooling water thermal capacity is quite high, the latent heat of the steam is taken away and they get condensed and accumulated at the bottom of jet condenser, and subsequently it is pumped to the hot well for the further use, right. And air which is coming with the steam, because steam when it is expanded, as I said earlier, by certain means the air managed to enter into the system. So, this air is liberated and this air is sent to the outside with air pump. So, this is about the jet level condenser which is counter flow type. Now, if you want to look at the parallel flow type of jet condenser, in that case steam and water move in same direction. So, that is parallel flow. So, the geometry remains almost same. At the bottom there is a pump, it goes to a well and the hot well, and definitely from hot well the water will go to the boiler, because after the condenser water goes to the boiler. Now, here the cooling water enters from here and steam enters from the top. In previous case the hot air was leaving from the top. Here the steam is entering the top, cooling water has lateral entry. There are certain taps here which allow the proper mixing of, in previous case also, which allow the proper mixing of steam and cooling water, right. After coming here there is a pump which removes the air, and steam, the condensate is collected at the bottom through a pump, it goes to the hot well, and from hot well it goes to the boiler. So, jet condenser, it does not require any pump, right. Sorry, it does not have any undercooling of water, it is designed such a way, because undercooling of water in any condenser is not required. In condenser it is required only that the latent heat is removed. Why? The reason being, suppose there is if again we will go for this temperature entropy diagram, 1, 2, 3. Now, we want steam at only a state 3, because when we will increase the pressure it will automatically become subcooled. But if the steam is left here, it is a two phase mixture, okay, that will drastically reduce the efficiency of the pump, or in fact two phase pumps are not available. Pumps are designed for single phase, that is water. So, if it is left here, it will drastically reduce it will become very difficult to operate the plant. So, we have to ensure that entire steam is condensed. Some undercooling will be there practically, right, but it has to be minimized, because anyway when we are compressing the steam, we are compressing the water, saturated water, it is turning into the subcooled water. So subcooling is not required here. So it should not be. So a good condenser design ensures that only latent heat of the steam is taken away, not the sensible heat. So here also in a parallel flow, it is collected and it is sent to the boiler. But here you see we need extra water. So water has to be plenty. In addition to the other purposes, here there plenty of the water is required for the purpose of condensation. Now regarding the efficiency, as you know, the counterflow processes are often more efficient than the parallel flow processes. So here also the parallel flow type of jet condenser is less efficient than the counterflow type of jet condenser. Now these are the low level jet condenser. Now there is one which is known as high level jet condenser. It is also known as barometric condenser. Now in this condenser, it is almost like a counter flow condenser, where there is a air pump which is at the top, air pump, right, and there is a leg. The height of this leg is equal to or more than 10.3 meters, which is equivalent to the 1 atmospheric pressure. Or 10.3 meters, we can say it is something like, if you can physically realize, it is a height of a, let us say, 10-storied building, not 10-story, 3-storied building. So because normally ceiling height is 10 feet or 3.3 something meters, so we can comfortably say it is 10.3 meter is the height of a 3-storied building. So this has to be ensured. Then there is a hot well here, right. Now cooling water is coming from the separate well through a pump, and from the pump it enters, the process is same, it enters the condenser. Here steam is coming from the exhaust, they get mixed and they are drained off. But here pump is not required. In this case pump is not required. That energy can be saved here, and normally water column is not more than 9.14 meter. For the most efficient jet type of high level jet type of condenser, water level is here is normally 9.14 meter, but still we take it more than 10.3 meters. After this jet type of condenser, there is another type of condenser which is known as ejector condenser. Now in ejector condenser, the cooling water enters from the top, and the cooling water pressure gauge is approximately 1.6 bar, slightly higher than the atmospheric pressure. And when it enters, there are nozzles which increase the velocity of the water, right. And here on this side there is an ejector system having a non-return valve. Non-return valve is a valve which allows the flow of the fluid in one direction only. If there is a reversal of flow, it will stop the flow. Non-flow of type of valve is provided here, so that in case of reverse flow, the water does not enter the engine or does not enter the turbine. So non-stop valve is provided here. There is an ejector system, and after that there is a diverging part, and after diverging part there is a collection of fluid. So the water enters from this side with a very high velocity. The number of nozzles are provided which further increase the velocity of water. Ejection system is here, through which system the steam enters, it gets mixed with the water. Subsequently the latent heat of the steam is transferred to the water, which increases the sensible heat of the water. Both of them get mixed and they are condensed in a pan. Okay, this is the steam ejector system. Now we will come to the most popular condensing device, that is surface condenser. Now surface condenser, there is a shell. In a surface condenser there is a shell, and shell has number of tubes, right, and cooling water, it flows inside a tube. There are tubes the cooling water flows inside the tube and shell is filled with the steam, right. So, it is extension of double pipe heat exchanger. Double pipe heat exchanger, there is a single tube. In surface condenser, there is a bundle of tubes. Now, what happens? Due to leakage, as I mentioned earlier, due to leakage from any joint or from any wall, because this entire condenser is a very low pressure, is at very low pressure. It is approximately 0.1 bar pressure, right? Or from joint or from this compensating water or makeup water, the air happens to enter in the condenser. When air enters the compressor, what happens? The air, the steam, what is happening here in this condenser, surface condenser, the cooling water is flowing inside the tube. It is surrounded by the steam. When hot steam is coming into the contact with the surface, which is at lower temperature, it transmits heat to the surface, and this is a copper tube, and from the surface it goes to the cooling water, and temperature of cooling water rises, or it is mCp delta T obviously, and this comes from the latent heat of condensing steam. Now, if the air is mixed with this steam, air will not condense. What is going to happen? Air will envelop this tube. So, this is the tube. A thin layer of air will envelop this tube, because this is the lowest pressure zone in the entire system. In the condenser itself, the vicinity of the tube is the lowest pressure zone in the condenser. So, here the thin layer of a cloud of air will be formed around the tube. Now, this cloud of air will prevent the heat transfer, or it will hamper the heat transfer. If there is not sufficient heat transfer in a condenser, the pressure of condenser will rise. There are many reasons in the rise of the pressure of the condenser. Suppose cooling water flow rate is low, in that case also the condenser pressure is high. If the air is mixed with the steam, in that case also the condenser pressure will rise, right. So, this is we will discuss it later on. So, here as per the construction of the surface condenser, there is a bundle of tubes, right, and the tubes are connected to the tube plate. So, if you look at the end view is going to be like this. There is a plate and there are number of tubes which are embedded in the plates, right. There is a water box on this side, there is a water box on this side as well, right, and water is entering from, let us say, from this side. First of all, it will not go to this side, there is a partition. So, water will move in this direction from the bottom, right. Then this is filled with water, right, and then water will take a U-turn and it will again flow in this direction, and after taking heat from all the tubes, it will leave from here, right. This is upflow, this is upflow. If you invert the flow, it will become downflow. Water entering from here and leaving from here, it will become downflow, right. So, in this condenser, the advantage is pure condensation is possible. We can easily design a condenser where only phase change of steam to water is taking place. Low quality of cooling water can be used in surface condenser, and high vacuum efficiency can be maintained. High vacuum efficiency, what I mean to say total pressure in the condenser will be pressure of the steam plus pressure of the air, right. So, ideally it should be the pressure of the steam. So, total pressure should be pressure of steam, because air has been added. So, the pressure inside the condenser has increased. So, if you take the ratio of these two, pressure of steam divided by pressure of steam plus pressure of air, this will give you the vacuum efficiency of the condenser. If the pressure of the air is 0, then vacuum efficiency of the condenser is 100%. Now, there are certain disadvantages also for the surface condensers. First of all, large area is required, large volume of water, so large volume of water is required if you compare with a direct contact or mixing type of condenser. Construction is also not simple. I mean, it is a complicated construction. Skilled worker is required to operate the surface condenser. Maintenance cost is also high for surface, but still, apart from these disadvantages, the surface condensers are used in a power plant. So, when we design a condenser, the minimum requirement for a good condenser, the minimum requirement of the good condenser is during the supply the pressure drop has to be minimum. During the supply of water, the pressure drop has to be minimum. Quick removal of condensate. Condensate should not accumulate in the condenser shell because it will hamper the heat transfer. So, quick removal of condensate, right? Low resistance in water tube. Low resistance of flow in a water tube. Now, here if you take tubes of smaller diameter, resistance is more, at the same time inside tube heat transfer coefficient will also high. If you take large diameter tube, resistance will be less, but at the same time inside tube heat transfer coefficient will be low. So, the designer has to always trade off. So, here also designer has to trade off what should be the diameter, optimum diameter of the tube. In this case, surface condensers, because they are not insulated, often not insulated, so the heat loss through the condenser wall by convection or radiation should be, or convection and conduction should be minimum. Leakage of air is main issue. So, air leakage has to be minimum, it has to be minimized in a surface condenser. But it cannot, the possibility cannot be made absolute zero, because air anyhow air will enter the condenser because it is running at a very high vacuum. Now, there are certain condensers which are known as evaporative condenser. In evaporative condensers, the steam flows inside the tube and it is surrounded by the cooling water. It is reverse of surface condensers, right. So, there are two types of condenser. One is downflow. In downflow condenser, there is a shell, there is a bunch of tubes, right, and the steam and air, they enter from the top, and steam and air, they come from the top. Another type of condenser is evaporative type of condenser, right. In evaporative condenser, the steam flows inside the tube and it is surrounded by the water, right. So, it is reverse of surface condensers. Now, there is, as I said earlier, there is a loss of vacuum which is major concern in surface condensers. So, loss of vacuum may be due to air leakage, loss of vacuum may be low water flow rate, cooling water flow rate. Okay. Loss of vacuum may be hamper in heat transfer due to scale formation. This may also hamper the heat transfer and may cause rise in the pressure in the or if there is an ejector jet in a condenser. So, the purpose of the ejector jet is to periodically remove the air and steam mixture from the condenser. So, if periodically if it is jammed or it is blocked, in that case also the pressure in the condenser will rise. That is all for today. Thank you very much.